Hi there. This video is about electrical potential. So you should have gotten from the sub a little note sheet that you pasted in your notebook to make this a little bit easier and less notes for you to write. So here we go. So electrical potential is this idea of voltage. Electrical potential and voltage are really the same thing. There are many different voltages we get out of things. Here's some fun ones for you. The alkaline battery that we use all the time, those AA's, is only 1.5 volts. I like the electric eel, considering that each of them is 0.15 volts, but you have a 5,000 cells and a 6-foot eel. That leaves at 750 volts. You're not going to make it. So what we're going to be able to calculate is the battery that we drew, or any battery that you want to make, how much voltage do we actually get out of this. Here's what you have on your note sheet. Let me take you through each of these terms here. Electrical potential. Electrical potential is that fancy word for voltage. It's measured in volts. It's just the idea that the cell's ability to produce an electric current. It's the ability of the chemicals to produce electrons, for electrons to flow on the wire and have that push. Remember, voltage is about the pushing of electrons from one side to the other. That's electrical potential. Electrical potential, voltage, same thing. And what we're going to do is we're going to actually calculate how much voltage it is. And when we calculate it for any battery we have, that's when we calculate the standard cell potential, which is symbolized by this. That zero thing is where the standard comes from. Cell, clearly cell potential, and E, this is where we get the potential part, the voltage. So notice one thing here is that we're going to be calculating these at 1 molar. So we know that the buckets will have a certain amount of solution, and if you want to use the standard cell potential, it'll be assuming that each of your buckets have 1 molar of each of the iron solution like we drew and the copper solution that we drew. Okay, so here's the equation for that. We're going to run through it in a second. But the other term that's inside of here, the E cell is what we just covered. That's the voltage you get for your battery. And these terms here are called the reduction potentials. The tendency of the half reaction to occur as a reduction. So the E reduction potential for the cathode minus the reduction potential of the anode. Let me show you the reduction potentials. You should have gotten a copy of this sheet from the sub. And you can see that we've got lots of different half reactions. And yes, you'll be able to use this on the test. So on the test, I'll give you an activity series as well as this chart. So you just have to know how to use it. So you can see that every single reaction that's on this list has electrons on the reactant side. Check it out. All the electrons are on the reactant side, which means every single thing is written as a reduction. That's why it's called the standard reduction potential. If you have a negative sign, that means it doesn't like to do that. So check it out. Lithium gaining electrons. If you look at your activity series, lithium hates electrons. He does not want to do that. You're going to have a negative sign because you have to input energy to make it happen. Check out the very bottom here. The left side is negative and the right side, right column, is positive. Check out the very bottom one. We've got fluorine here. Fluorine wants to gain electrons. Oh yes, fluorine is the most electronegative element on the periodic table. So does he want to gain electrons? Yes, that's why it's a positive value. You don't have to force it to do it. It wants to do it. All positive values are things that want to happen. And the negative values are there because, well, they don't really want to, but they'll do it if you want. They'll want them to, if you put them in the right spot. And you can see our 0 mark here. Our standard is based on actually hydrogen. Hydrogen, positive ions creating hydrogen gas. That's our standard, how we compare all these things to. And that standard is how we get our voltage scale. Okay, so that's what the chart is. What I want to do is calculate my standard cell potential that we did for our battery. So here's my picture. You can see that I erased my balanced equation at the bottom because I needed some space. I'm hoping you have some sort of space hidden in there somewhere that you can add this to. If not, just put in your notes and just know that you've got to reference that. Handily, you can even paste these notes onto the back of your drawing here, but that's up to you. Okay, so what we're going to do is our equation that we have. E cell equals the reduction potential of the cathode minus the reduction potential of the anode. It's always cathode minus anode. Okay, my cathode, as we labeled here, my cathode is my copper side. So I'm going to look on the chart for this guy. And my anode is my iron side, so I'm going to look for this guy. So check out your chart. I am going to look for the copper one first. So if I look for the copper one, it's at the very top. I'm hoping you can see my pen, at the very top on the right. Notice that there's 2 coppers there actually. One copper goes from a 2+ to a 1+. That is not the copper we have here. Our copper is going to a 2 plus to a neutral. So we want to use the reduction potential 0.3419. So put that in here, 0.3419 minus, now I need my anode number. That means I'm trying to find my iron one. My iron one is way at the bottom on the left, just above hydrogen, way at the bottom on the left. I can see my reduction potential for that is a negative 0.037. Negative 0.037. I'm going to stop right here. I'm using the equation, so all you do when you use the equation is you take the numbers from the chart and you put it right in there. You don't change any signs, you don't do anything fancy, you just put it in the equation. I know that some of you might be thinking, well, if you look at this iron equation here, Staub, it's the opposite of what you have on the reduction potential sheet, so shouldn't you give it a flippy-flippy? Okay, this negative sign here does the flippy-flippy for you. So I want you to stop being smart, because you're totally right. But what you want to do if you're going to use this equation is you just take the numbers from the chart and you put it in the equation, and then you stop thinking. Okay? Okay, so now if you take 0.3419 minus a negative 0.037, it's really like adding, and I will get a 0.3789. Sig fig wise, the chart has infinite sig figs really, and so whatever you do for sig figs, I'll count it right. There's really no sig figs I can grade for here. But what I can grade is that you've got units. My units for this is volts, voltage. So from this battery that we made, if it's at a 1 molar solution, we would create 0.3789 volts. That tells us how much push it goes from one side to the other side. Okay? Alright, not so bad, right? I gotta add one more thing to our drawing here. I'm hoping you have a spot for that too. A shorthand configuration, because you might be thinking, wow, the ChemGots do not like to draw this much and write this much information. You're right, they totally don't. They like to shorten it. And the way that they shorten it is by taking whatever they're doing oxidized right here and show that it loses 3 electrons. And then on the other side, they're going to have the copper, that's my reduced part, making copper solid. This would be the shorthand notation for a voltaic cell. You can see that it shows on the left side who's oxidized. They put a line there to show whose iron is going to iron 3+. They put the double lines in to show that, separating the 2 buckets. And then on the right side, it shows the reduction part, where copper 2+ is making the copper solid. So what I wrote in blue there is the shorthand notation. ChemGots like that better. Okay, let's go back to this here. So thinking about this list, which one do you think would make the best battery of all the batteries that you'd have? According to this list, you'd want to have somebody who really hates electrons, that'd be lithium, losing his electrons to really create somebody who loves electrons, fluorine. So the best battery according to this table would be a fluorine lithium battery. Sounds pretty good, right? Oh, that looks awful. It looks way better on your sheet. It looks good here. We'll go with this. So let's find the cell potential for this following part. There we go. Why don't you take a moment and try doing it yourself as I catch up. Okay, this is going to allow me to write on it. So I'm going to look up on my chart the 2 numbers for this. I looked at magnesium and I found on the chart it's a negative 2.372. I looked up the zinc and I saw it's a negative 0.7618. So what I'm going to do is subtract the cathode minus the anode to get my E cell, or my standard cell potential, which is the voltage of the battery. So in this battery, my cathode is the zinc one. So I'm going to take 0.7618, the negative 0.7618, and subtract from it the negative 2.372. If I calculate that out, it's really subtracting negative is like adding a positive. I get 1.6102 V for volts. And that's my answer. Alright. You got this last one on your note sheet. I'd like you to try this on your own, and then in the Google form you'll find the answer. And if you have any questions, please add it into the Google form. Thank you.